Okay. Hello. So for anyone who's watching from home, we're doing beta-oxidation biochem for the first hour, and then for physiology, we'll be getting into Clotting Cascade. All right. So any questions on the side for anyone who is live, I'll go ahead and check those at the end. And yeah, just type them in. All right. So.
What are you doing
now? YouTube. So. What did we have come up in biochem, or preferably biochem, one topic for now, but anything come up that was confusing besides just going over the whole thing? Like what's the pathway and that sort of thing. Any questions come up? No? All right. So I'll ask you one then. What is the purpose of beta oxidation? What's happening in the pathway in layman's terms? To use fat for energy, yes. So we are taking fat, breaking it down. So our beginning product is going to be a fatty acid. That's going to be coming out of adipose cells. That'll go through a whole bunch of stuff, find its way to getting inside mitochondria, inside liver cells, as well as elsewhere that can do this. And what is the end molecule that's going to be shoved into the TCA cycle? What do we end up cutting that fatty acid into? A bunch of?
Acetyl-CoA?
Acetyl-CoA, yes. All right, so if you can hold on to those two pieces, then all the stuff in the middle can make a lot more sense. Because this is one of those pathways that it isn't too bad unless it gets lost. So, let's see. Let's go ahead and do a little bit of fun here. So, all right, so the blue box is an adipose cell, aka fat. All right, and what hormone is, so we're trying to break down fat, so are we in fed state or fasting state? Fasting or starvation. So what hormone is high in fasting or starvation state?
Glucagon. Yeah.
Glucagon. So we have glucagon. And then we have one other hormone. Does anyone know what other hormone might be a triggering hormone for trying to get more energy into the bloodstream?
Insulin?
Cortisol is, that's
Is it insulin? No.
trying to get more energy into the bloodstream.
Insulin?
Cortisol is, that's
Is it insulin? No. Epinephrine?
epinephrine. And I'm going to throw cortisol up as well, because cortisol is a funny hormone, and yes, it does bring more food into the bloodstream, but it's one of those ones that will focus on glucagon and epi because they're straightforward. All right, so there's going to be a receptor for these hormones, and when that receptor is turned on inside the fat cell, it's going to go ahead and turn on somebody who is named after the fact that he's sensitive to hormone levels in the blood. He is an enzyme called hormone sensitive lipase. So hormone sensitive lipase is waiting for hormones to tell it on to cut up lipids, lipase. Hormone sensitive lipase will take the tags, triacylglycerols, that have been stored in the fat cells, and it'll cut them up into the two parts of tags. Does anyone know what tags are made up of? There's glycerol,
fatty acids,
and fatty acids. Excellent. So we have a glycerol backbone. I'll just put a G in there for glycerol. And these squiggles represent fatty acids. And now they are free fatty acids, so FFA. Okay, so we just took them apart, and these fatty acids get thrown into the bloodstream. So, in the bloodstream, we have a protein that is kind of our universal carrier. Lots of things go through the blood that are not hydrophilic, and the blood is water-based, and so it's a very hydrophilic place. So if you stick something in the blood that's hydrophobic, it's going to try and get as far away from the water as possible. That means it would be mushed into the side of the blood vessel and build up there, and it wouldn't transport very well. Fat doesn't like water, so we need something to carry it. Otherwise, it'll build up on the edges of the blood vessel. Make sense? Okay, so some of it does manage to go through on its own. It's just not very efficient. So we have this protein that is called albumin. And albumin carries the free fatty acids. And since albumin is so good at going through the blood, it's very hydrophilic. Even though it has some fatty acids on it, it still goes through the blood nice and smooth. Albumin also can carry things that don't relate to this pathway. Albumin, if you ever don't know what carrier protein is being used, it's probably albumin. There are some specialized ones, but a lot of the time, albumin just carries like a dozen different things. All right, so albumin will then come down. We're going to throw albumin. Albumin's going to throw the free fatty acids into the liver. All right. Ooh, that was. Well, we know what my favorite color is. First one out. All right. All right, so this is going to be hepatocyte. Technically, other cells can receive fat as well, but liver is the big guy for this. So the liver is going to receive the free fatty acids, and before we go on for what happens in the liver for the processing of these guys, let's go ahead and do a review. Hormones that come, what happens inside the fat cell, how do we transport it? Those are the three questions. See if you can answer them without looking at any notes. Once you're done writing, and then, would you like me to, I've been asked a couple times when I ask these questions, would you like me to just say it really quick, or do you prefer to do it your own way? Did that make sense?
Can you say it?
Okay, so the way that I would go ahead and answer this is 3 hormones that come in: glucagon, epinephrine, cortisol, turn on the fat cell receptor. We go inside the fat cell, hormone sensitive, because it was turned on by hormones. Lipase cuts tags into 2 parts, glycerol and free fatty acids. Moving outside the cell for part 3, free fatty acids hitch a ride on albumin down to the liver cell. So,
She has ACTH on her slides. Are you considering that as cortisol?
ACTH, adrenocorticotropin releasing hormone, ACTH. Let's go ahead and throw ACTH leads to cortisol. So, thank you. Let's toss that up there. If that's what she wants on the slides, then let's do that. I think cortisol is we'll leave it at ACTH. That's what she's got. And by the way, if anyone, thank you for that. If I ever go against what the slides say, please correct me so that everyone else doesn't have the foot and mouth taste for the rest of the session. All right, so go ahead and see if you can recall without looking at notes. We'll give this about 30 seconds. Ready to go. About 5 more seconds. All right. Good. Any questions? Question?
What happens to glycerol?
So the glycerol has its own separate pathway. We'll talk about that after we get through the rest of this. I find it easiest to keep them separate. The short answer is it eventually gets recycled.
So the blue box is a cell?
Yes, the blue box is a fat cell.
Okay.
All right. So moving to, that was all what I call part one. Part two is once it's inside the liver cell. We were calling this a free fatty acid beforehand. Free fatty acids can be called a number of things. Another name for a free fatty acid, same molecule, is an acyl group. So not acetyl, but acyl. There's no T in it. All right, and the molecules, acyl, inside the liver are named after, they use the acyl name in all of their names, and so that's why we're going to go ahead and start thinking of it in this name. So we have an acyl group, and we are going to have an enzyme called acyl-CoA synthetase. And that enzyme is going to grab the acyl group and stick a CoAsh on the end, a CoA. All right. Synthetase, it has a T right here, where synthases are free. Synthetases cost ATP. So whenever you see an enzyme that has synthetase, it means ATP is being used. And in this case, you're actually using 2 ATP. You're using 2 phosphates. ATP goes down to, so it goes ATP, ADP, AMP, tri, di, mono. This guy actually knocks 2 phosphates off, so it's costing 2. We just call it 2 ATP because we always talk about ATP as though they're dollars rather than molecules, so it costs 2 ATP. But what it's actually doing is taking 2 phosphates off of the same ATP and turning it into an AMP. If you just remember it costs 2 ATP, you're good. I just know that I always have someone ask, like, well, why is there only one of them there? It's because it takes 2 of them off the same guy. All right.
The acyl and the CoA there, what is that?
So the squiggle is an acyl group that we started with. The CoA is something that the synthetase attached to the end of it. And so now it's an acyl CoA, and that's the name of the molecule. So acyl CoA, that's what that guy's name is. All right, so much for the outside of the mitochondria. Now we need to go inside the mitochondria and mitochondria. This is where we're going to go ahead and have some pets. We have cat, cat1, and cat2. All right, so carnitine is the name of a protein. So I'm just going to make carnitine this little purple squiggle. And this name is the enzyme that is attached to the mitochondrial membrane here. On the outside one, it's cat1, carnitine acyl transferase. And then cat2, carnitine acyl transferase 2, is on the inner membrane of the mitochondria. So by the name, we can tell it's going to do transfer, meaning it's going to swap locations of a molecule. Now what it's swapping is named in the rest of it, carnitine and an acyl group. So it's going to be swapping carnitine onto the acyl. Simply said, it pops the CoA off and it puts the carnitine on. That's it. One more time. The acyl CoA comes down to cat1, it pops the CoA off and puts a carnitine on. So now it is acyl carnitine. Okay? Then the acyl carnitine is allowed to go through the mitochondrial membrane And it arrives on the other side, and Cat2 takes the carnitine off and puts a CoA on. So it just undoes what the first guy did. The only reason you stick a carnitine on is so that you can regulate how many fatty acids are going into the mitochondria. Because you can have fatty acids that are very useful for other jobs that you don't want to burn. And this makes sure that only the ones that you want to burn and are tagged very carefully with carnitine will go through into the burn state inside the mitochondria. Make sense? Any questions? No? Okay. So we end up with acyl-CoA, and we just took off a carnitine. And CoA is just in the cytosol, both outside and inside, so that's where that comes from. All right. Before we get into more stuff, to tell the story, acyl group comes into the liver. We stick a cap on it to say we want to burn this one, and then it's acyl-CoA, which was made by acyl-CoA synthetase, crossing to ATP. That capped acyl group can be acted on by Cat1, which will swap it for a carnitine to make so that it will definitely go through the mitochondria. And then on the other side, we swap it back to an acyl-CoA because it's already made it across. It doesn't need the carnitine anymore. Okay? So add a CoA, swap it to a carnitine, swap it back. That's pretty much what's going on. All right. Any segments unclear before we do a review?
What was the point of putting the CoA on there?
Putting the CoA up here.
On the silver?
So the point of the CoA right here is because there are lots of fatty acids in the liver. And so if we're in a fasting state, that's when this enzyme, acyl-CoA synthetase, will be on. And so we'll stick CoAs on fatty acids in the fasting state. How does the cell know it? How does...
So each one of the acyl groups to get a CoA?
Yes.
Okay.
But that won't happen in the fed state. So this molecule is basically confirming, yes, we're in the fasting state. Let's tag a certain number of acyl groups as burnable.
Okay.
And then the carnitine is only
only to go into the mitochondria.
Exactly.
Okay.
The Cat1 and 2 will only move the ones that are already tagged into the mitochondria. So it's just tagging it for burning.
And those are the same two that lets it out.
It's the same two that lets come again.
You said it would leave something on the mitochondria? They go
So
out through that the same way?
nothing actually leaves the mitochondria. You're just, I think I know what it was. You swap a carnitine onto it, and then the carnitine swaps off, and the carnitine leaves, but it's still inside the mitochondria.
Okay.
That's probably what the word leave was.
Leave, okay.
So make it, swap it back. It's the easy way to remember.
Acyl-CoA in the liver and mitochondria, but in the mitochondria it needs the carnitine to get in, and then it kicks it off.
The carnitine is the bus pass to get through, exactly. All right, and then once it's in there, if you have acyl-CoA inside the mitochondria, then you're going to go ahead and do burning. I do want to give you a chance to do recall on this, because if you can make it stick, then this is twice as valuable time. Understanding is good, memory is good, both together means you pass. So let's go ahead and take 20 seconds to try and say what happens inside the liver as soon as the acyl group arrives. A few more seconds. All right.
Sorry, where's the carnitine coming from?
So carnitine, like CoA, is just floating around, both inside and outside the mitochondria in the cytosol. So it's just readily available to be grabbed.
Is carnitine a protein?
Yep. You'll sometimes see people saying, this supplement has carnitine. And that's usually for sports supplements so that you get energy faster and that sort of thing. And if you have a shortage of carnitine, then that can actually help, according to some doctors, who I believe, but I haven't read the studies, so I'm just going to say according to other doctors. All right, any other questions? Schmette. All right, so part 1, part 2, now part 3. So I'm going to make our mitochondria a lot bigger. Oh, jeepers. All right. So, beta-oxidation. So this has 4 steps, and let's see, beta-oxidation proper is this 4-step cycle where you have an acyl group come in, acyl-CoA, and that's going to become enoyl. That's going to become. Okay, so I'm going to need your guys' help with the slides because these names I occasionally jumble, and I don't want to do that to you guys. So the first one, you start from acyl-CoA, and that's going to have an enzyme, I believe it's called acyl-CoA dehydrogenase, yes? Do we happen to have the slides available? There should be.
I have this, but it doesn't have the enzymes on it, actually.
Dehydrogenase. Appreciate that. And that'll turn it into trans-enoyl. Ugh, that's illegible even to me. Trans-enoyl, I believe it's acyl-CoA after that. Note that this has trans, it is a trans fat. So if some people, so trans fats are things that we shouldn't eat because we have very great difficulty in breaking them down. But sometimes I've heard debates pop up where people are like, oh, we can break down trans fats. No, we can't. Yes, we can. The truth is we can break down some, but the kind that we find in the diet, if anyone ever tries to say we can break those down, those we really, really struggle. Not all trans fats are the same, but the ones that we tend to find in food sources are not equivalent with this one. Same family, we can break this down, we struggle to break down others, just in case that comes up as a question, because I've had that come up with people trying to argue their dietary choices as being wiser than they were.
Taylor, what's the DH in the box?
Dehydrogenase, just an abbreviation. And the little arrow is pointing to acyl-CoA, meaning it's an acyl-CoA dehydrogenase. That's my shorthand.
Oh, so it's an enzyme?
Mm-hmm. Oh, I'm sorry. All right. So when I box something, that means it's an enzyme. And if I have an arrow to something, it's basically ditto marks, except pointing to the thing that has the ditto marks on it. Okay? All right. Thanks for asking that. Occasionally I forget to do a recap at the beginning. All right, so trans-enoyl. Acyl-CoA is what I believe is at the end here. Nothing else is called trans-enoyl, so it's not going to get confused with anything else. This is going to have an enzyme. I believe that's trans-enoyl hydratase. Yes? Awesome, thanks. So that thing, hydratase. And it's hydratase, not hydrolase. Thanks. All right. All right. And that will make the molecule. Can you give me the molecule on this one?
Hydroxyacyl-CoA.
hydroxy, okay. Hydroxy acyl-CoA. They all end in acyl-CoA pretty much. All right. And then this second guy is going to be a hydroxy acyl-CoA dehydrogenase. So what I want to point out here, she's usually, unless an enzyme is part of disease, it's okay to be a little bit ish. I mean, you want to know it, but a lot of them will fall out of your memory. What I do want to point out, though, are the two dehydrogenases are step 1 and step 3, and that's where some of the energy comes from. Because a dehydrogenase means it's taking a hydrogen off of the molecule and putting it somewhere else. It's putting it onto a hydrogen receiver, which is NADH or FADH. Which B vitamins are those? NADH, which B vitamin? 3. FADH, which B vitamin? 2. All right. So in green, since we're earning it, we get right here 1 NADH created by this dehydrogenase taking a hydrogen off of the acyl-CoA and putting it on to the NAD, which becomes NADH. Down here, we have same thing happening, except it's giving it to an FAD to make FADH2. It's FADH to FADH2. So these are our two energy inputs. What's up?
On the slide, it shows the opposite.
Oh, FADH, the first one?
Yeah.
Thanks. FADH.
Are there other names for that enzymes, like the transenol enzyme?
So the transenol,
Hydratase, are there other names?
I don't know of other names. If there's another name in the slides, that's the one you should go by. What is it?
I watched
know?
the Ninja Nerd video and I thought he called it proteinase, transprotein.
Transproteinase.
CROTO.
Yeah, I haven't heard that one before.
Beta-Oxidation.
Oh my gosh.
It's possible, so with the other enzyme that you brought up, it's possible that is, if we have a strange fatty acid come in that isn't just a straight acyl group saturated, and if it's an unsaturated fat, you have to send it through another process, and that is probably where that enzyme is, because then you have, instead of step 1, step 2, step 3, step 4, you have step 1, step 1.2, 1.3, 1.4, because it does this whole little loop to get ready before it goes and becomes transenol. And I can't draw the loop in without making it a huge mess.
All right, sorry to make it confusing.
No, I'm glad you brought that up, because we will want to know that this is the saturated fat cycle. If it is an unsaturated fat, you have extra steps stuck in right here, but Professor Yomi does not require you to know those steps. Just be aware that there are extra steps to make a fat saturated if it wasn't, and then send it through. Did that make sense?
I might have given you the wrong name then, because what does that go to?
Which that?
From hydroxyacyl-CoA.
Hydroxyacyl-CoA, that should go to a keto,
Yeah, beta-keto.
beta-keto-acyl-CoA.
Yeah, that's right.
Beta-acyl-keto-CoA. And the last enzyme, as I recall, is thiolase. And this is going to give us our third product. Okay, so we had two products so far in green, FADH, step 1, NADH, step 3, and then at step 4, thiolase is going to take this nicely prepared chain of, so let's zoom in here. Here's what, each of these circles represents a carbon, and I am making a fatty acid chain, because it's just carbon, 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 carbon. Thiolase, after all of the funny bits have been removed to make it look right, thiolase is just going to cut in between the terminal 2 carbons and the rest of the chain. And so these 2 carbons will float off free, and they are acetyl-CoA. And that's 1-acetyl-CoA. And then you send it through the cycle again, and you mess with these 2 carbons through all the enzymes, getting them ready. And then at the end of the second cycle, you'll do the same thing, cut it off there, you'll get another acetyl-CoA. And so that is the beta-oxidation cycle. Now, so for one cycle, you get 1 FADH, 1 NADH, and 1 acetyl-CoA typically. And so that's going to be, let's see, how many ATP does FADH2 give you? 1.5 is correct, and often it's rounded up to 2. You are correct, it's 1.5. I'm just going to simplify here. How about NADH? 3. 2.7, rounded to 3. How much does 1 acetyl-CoA give you once it's been chewed up through the TCA cycle? Acetyl-CoA will give you 10 to 12 with 1 acetyl-CoA. Okay? So, depending on how she asks the question, she could be asking for how much are you getting directly in beta-oxidation, or she could be saying how much are you getting including when the acetyl-CoA is chewed up. So you get 5 per cycle, roughly, 4 to 5. Directly in the beta-oxidation cycle, add 10 to 12, and she'll take the ish amounts into account for each cycle. And this is for all the cycles until the last cycle. If you'll notice, the last cycle, and I'm going to go ahead and get rid of this one because we'll talk about that later. The last cycle, when you do a cut, you formed not 1 new acetyl-CoA, but 2. Because there were 4, you cut that in half with a single cut, and all of a sudden you have 2 carbon molecules. So the last cycle gives you 2 acetyl-CoA, 20 to 24 ATP. All right, so question.
When you're looking at the ATP production for acetyl-CoA, what are you taking into account? Like all the NADH and FADH from TCA? Or?
Yes, so there's 3 NADH, 1 FADH2, 1 GTP, and then all those go through the electron transport chain. Yeah, not at all. All right, so all of this makes sense up to this point.
So, through the whole thing, it only cost us 2 ATP, at the beginning?
Yes, thank you for saying that, because that's the other thing that she might ask is, for this entire sequence, let's box the sequence. So here's the repeating sequence inside the purple box. That happens every time. Inside the blue box at the bottom, that's only the last time, right? Last time gives you an extra acetyl-CoA. So I'll just go ahead and write another acetyl-CoA. Now, very good point. You also have a one-time cost for the entire chain. It's not every cycle, it's only one time. So I'm going to write it up here in a blue box because it's once for the entire thing, and that's 2 ATP to add on the CoA. I'm going to say CoA costs 2 ATP. CoA 2 ATP. And that is -2. So to get your total cost, we are doing this stepwise because otherwise it's like there's a lot going on. you get your cycle, and depending on how long the chain is how many cycles you'll be able to go through. The last time you go through, you get an extra acetyl-CoA. And remember to take off the 2 ATP that you did to tag it for burning. There's a little bit of stuff going on there. Does that make sense? Are we good? Let's do a couple practice questions. Okay? So, if you had a 16 carbon fatty acid, how many cycles could it go through? We're not talking about ATP, just how many cycles would a 16 carbon fatty acid go through to be cut up entirely into 2 carbon molecules? Go ahead and think it. We'll give this another 10 seconds or so, and then we'll go ahead and take an answer. Anyone want to take a stab at it? 7. Excellent. So why not 8?
Because the last one is 2.
Yes, because the last one gives you 2 at once. And so that last cycle gives you, you get an extra one on the last guy so you don't have to go through it in 8th cycle. So the way that you can always do this, I find it makes the most sense if it makes sense. You can also just memorize half the number of carbons minus 1, but I find that that's easier to forget than like, oh yeah, the last one makes sense why you'd have 1 fewer times because you're getting double the product for the last cycle. All right, next question. If you had, actually let's just tag on to that one. No, I'm not going to do that to you yet. Not yet. How many ATP would you get out of a 10 carbon fatty acid? Including everything, acetyl-CoA and all. And go ahead and use 10, just to keep it simple. 10 per acetyl-CoA. That way you don't have to do math with a range. All right, anyone want to take a stab at it?
133?
So 133, any other answers? 133 is a little high. 75, so let's see, that's, all right, so we have a total of 5 acetyl-CoA will eventually come out. That's 50. We have 4 cycles.
Why is it 5? I don't know why I got 4, because I thought you said the last 2 was...
So the difference between the number of cycles and the number of resulting acetyl-CoA, that's probably what was going on there. So we know that it was a 10 molecule chain, so that's going to give us 5 acetyl-CoA, so that'll end up being 50. Next, we know it's 4 cycles, so 4 times 5 equals 20. So that gives us 70. And then 70, we have to remember that to tag this guy, we had a minus 2. And so 70 minus 2, 68. Make sense?
Remind me again, where do you get the 50? The acetyl-CoA?
Yeah, so first, if we have 10 carbons, we know acetyl-CoA is a 2 carbon molecule, so they're all going to end up in 2s. And there's 5 of those, yeah. And so that's the easiest one to do first. Then you go to the cycles next. and then you do the cost. It's actually easiest to go backwards.
Also, the 4 times 5 is from FADH and NADH?
The 4 is the number of cycles.
Yep.
The 5 is FADH and NADH put together.
Yeah, okay.
And then that gives us a total of 20.
Okay, 4 is number of cycles and 5 is the.
Every cycle gives you 5. So
Okay.
4 times
Okay.
4 cycles, 5 ATP each, total of 20.
Is she gonna ask questions like this?
Not in a way that's like a huge thing. There might be 2 out of, she does like 50 question tests, 40 question tests, something like that. So it's not going to be something that is going to kill you if it's difficult. Yeah.
Where did 50 come from?
50 came from the acetyl-CoA, 10 each.
Okay.
And she'll say, assume 10 unless she says otherwise. Because usually, and often, if I recall right, she actually says, assume 10 ATP per TCA cycle or something like that. But it's good to know.
Okay, Taylor, so acetyl-CoA goes in, and then it produces FADH and NADH. And then what were you saying about it cutting off? It just keeps cutting off too, right? But where did the acetyl-CoA equals 10 to 12 come from?
So the acetyl-CoA will then go to another pathway that we haven't gone into, the TCA cycle from last quarter.
Oh, okay.
And it goes through a bunch of steps there, citrate, isocitrate, alpha-ketoglutarate. It just goes through the whole, you might remember it as the citric acid cycle,
Yeah.
TCA cycle. That thing generates 10 ATP out of the acetyl-CoA, which is just shipped over there.
So the same 2 go through this and then the citric acid cycle?
So restating what I think you said,
Yeah.
acetyl-CoA gets cut up into acetyl-CoAs,
acetyl-CoA.
and then acetyl-CoA does some more stuff off the
There we
board
go,
to
that's
make
right.
more ATP in the, yeah.
So acetyl-CoA is another name for fat.
Acetyl-CoA is another name for
Without the
fat.
T.
Yep.
And when you add the T, then it's what?
Acetyl-CoA,
And
and it's a 2. I remember
That's a 2
acetyl,
carbon.
the one that has a T in it, is a 2 carbon molecule.
Oh,
That's
okay.
why it has a T. It's not really, but it is.
Yeah, okay, that helps.
So acetyl, 2 carbons. All right. Let's do one more practice question on, question. Go ahead.
Can you just, what was the arrow coming off of the ovaries?
Arrow coming off of the thiolase.
Yeah.
That was just showing that the thiolase was going to make acetyl-CoA, and then I drew a bunch of math. So it's pointing to the acetyl-CoA going off towards the TCA cycle. All right. Any other questions before we do one more question that I throw back at you? All right, go ahead and work it out. And remember, it's easiest to go from acetyl-CoA to cycles to that little cost at the top. If you do it that way, way easier. All right, go ahead and do it for a 12 carbon molecule. I don't want to do it too close to 10. Let's do a 6 carbon molecule. Ready, go. 6 carbon acyl group. Take a few more seconds. All right, let's crunch through this. We have 6 carbons. I'm just going to make a box over here where we're continuing. 6 carbons. That gives us how many acetyl-CoA?
33.
3. And that's how many per acetyl-CoA? How many ATP for each acetyl-CoA? 10. So we get 3 times 10, 30. How many cycles?
2.
2, good. And the cycles thing, she might ask you a cycles question without the math. She'll ask you a math one probably. She'll ask you a cycles one probably. And so math is only 1 or 2, but the cycles is another one. I don't remember for sure, but I feel like she will. I seem to recall the cycles one. I think I remember hearing like a dozen students after the test. It was great. So lost my train of thought. Mockery does that, unfortunately. I shouldn't. All right. And so 5 per cycle gives us 10. What's the last step?
-2.
-2. Where does the -2 come from? Activation cost. That's how she'll say it, is either activation or CoA translocation or something. She'll say activation. And so if the word activation doesn't mean anything to you, that can throw you. Activation. So we end up with 38. All right, brilliant. So now I have one last curveball to throw. What happens if you have an odd chain fatty acid? Everything we've done up to this point stays the same except the last cut. The last cut, I'm going to get rid of these guys. The last cut doesn't give you 2 acetyl-CoA anymore. It gives you 1 acetyl-CoA and one weird thing. Weird thing with 3 carbons. It's similar to a glycerol because glycerol has 3 carbons. What it is called is less important than what it becomes is another 3-carbon molecule called pyruvate. And so it goes through a few steps to become pyruvate, but this is the one time, the only time, that fatty acids give you something that can become glucose. So all the rest of this was completely inside the mitochondria. You're going to burn it, you're going to break it, you might put it together. Acetyl-CoA can become a couple other things, but it can't go back up to glucose without costing more than the fat was giving it. And there's a reason for that I think we went over in the TCA cycle. We can hit it again another time if you want, but just trust me, all the fat stuff cannot become glucose except for this one exception. And that's a favorite question no matter who your professor is, and it's also important for clinical reasons. This is why the keto diet actually is a thing, because you can't make glucose out of fat. And if that fact wasn't true, keto diet wouldn't do anything to your glucose levels. So, pyruvate is what it can become, and does anyone who has the slides available remember what the 3-carbon molecule is actually called? I don't think that they usually ask that, but for the sake of completeness.
It's propionyl.
Propionyl.
I've got CoA.
Propionyl. CoA. Yeah, thank you. And propionyl-CoA will become pyruvate. And so, and then that'll go and do its glucose thing, yada, yada, yada. And so in this case, how many acetyl-CoA did we get in the last cycle? 1, not 2. Because one of them is going to fly off and become glucose now, and it's like, thanks for nothing, it's gone. And so you would, if it's odd, you don't get an extra acetyl-CoA at the last cycle. Okay? All right. Any questions before we do step 1, step 2, and step 3 review, and then close up the biochem? And we'll do questions after that as well. Before we do the review, does anyone want to do more math questions? Maybe one with an odd chain? Or do you feel odd chain? All right. So go ahead and work it out for a 19-carbon fatty acid. Take another 10, 15. Or longer if we need it. I don't know if the board is even visible to you guys, so let's. Hopefully that's a little better. Welcome, welcome. Come on in. We need a little more time, or are we good? We good? A little more time? All right, let's go through it then. So, for the biochems, all right, so 19, how many acetyl-CoA are we going to get out of a 19 carbon molecule? 8 is correct. So, the way that I like to do is figure it out as though it was even, and then just take one away. So, 8. How many ATP do we get per acetyl-CoA? 10 per acetyl-CoA. So that's a total of 80. How many cycles are we going to go through?
8.
8. When it's an odd chain, the numbers are the same. And how many ATP per cycle?
5.
5. That is the squonky looking 5. The second one I drew isn't much better. You know you're in the right room. All right. And the cost.
-2.
-2. I know you know it, but I'm making you say it repeatedly so that it sticks. All right. So we got 120 minus 2. That's 118. 118 would be your total energy gain plus 1 propionyl-CoA, which is not going to be an energy thing. Flies off to become glucose and energy elsewhere, but we don't care about it because it's not energy here. All right.
How did you figure out how many cycles?
So the cycles, what I like to do is work out the cycles as though it was one less. So it's an 18 carbon molecule, and then that's 9 cycles, except you get 2 on the last one, so 8 cycles. Did that make any sense, or should I say that in a more English kind of a way rather than gibberish? If you take the odd chain and just make it into the next lowest even chain, and then figure out cycles for that as though it were the even chain, that'll still be good. The math trick, if you want it, is 1/2 of that is 9 minus 1 equals 8. So half of this number minus 1 will always give you the cycles. I like to also double check to make sure I'm remembering the right little trick, because they throw like 4 math tricks at you in the same little 2 lectures, and it's like, which one goes where? And I still make that sound when I try to remember that, until I remember the 2-for-1 last cycle. You get 2 acetyl-CoA for 1 SNP, and then that makes so that you can be for sure, so there should be 1 less cycle than there are acetyl-CoA. All right. With our math beautifully done, let's go ahead and do a review on part 1, and then we'll do a review on part 2, and then we'll do a review on part 3. This will help it stick. So, inside of part 1, if you guys want to go ahead, I'll for this particular review, I'll go ahead and ask you prompting questions to go through it. See if you can ask the questions as we go, and try not to look at any notes. Okay?
Real quick, is there a rate limiting step?
Rate limiting step. Yes, thank you. Acyl-CoA synthetase is the rate limiting step. By the way, cool, very rough rule of thumb. Usually energy costing steps are the rate limiting steps. So if you're ever like, I don't know, just hit the one that costs the most energy. I only make these sounds because I make them all the time myself. So it's like, yeah. It's the nice thing about multiple choice. I know some Latin. That makes sense. All right. Okay, gonna start the prompting questions. Eyes off your notes, so it's active recall if you would like, however you want to do it, really. Okay, so this whole process starts when we are in the fasting or starvation state, and some hormones are out in the blood. Name at least 2 hormones that are in the blood that might be going to the fat cells to try and pull fat out of them. We'll give this one about 5 to 6 seconds. All right, hormones you could have chosen from: glucagon, epinephrine, ACTH, or cortisol. All right, in the fat cell, what's going on? I'm just going to ask you to go through the whole thing inside there. Okay, so that was hormone-sensitive lipase. It grabs tags and rips them apart. Glycerol to one side, free fatty acids to the other. All right, the free fatty acids are going to go ahead and leave the fat cell and go into the bloodstream, where they are going to be assisted by something to get somewhere. What is that something, and where is that somewhere? All right, that something is albumin, and it's going to arrive at the liver and dump all of the fatty acids into the liver. This was part 1. I would see if you can go through that story in your head, make it nice and comfy, and then you're good. Part 2, once it is in the liver, it's called a what group? Acyl group, meaning a fatty acid. It's just a synonym. All right, first thing we're going to do is activate it. How? What do we stick on? What is the enzyme? We stick a CoA on with the enzyme acyl-CoA synthetase, meaning we are synthesizing acyl-CoA. So it makes sense that that's what the enzyme is named that's making it. And it costs 2 ATP and is the rate limiting step. Next, we need to get it into the mitochondria. How do we do this? I'll give you a hint. This is where the cats are involved. Cat 1, cat 2. What's going on with them? All right, so cat 1 pops a CoA off, puts the carnitine on. That lets it go through the bus system, so to speak. Pops out the acyl carnitine, comes out the other side. Pop the carnitine off, put a CoA back on. That's it. Cat 1 is on the outside, cat 2 is on the inside. All right, then we get to beta-oxidation, and here what you really want to remember is mainly the energy that's produced. It is good if you know the molecules. So for those, which steps generate energy? And then step 1, step 3, generate energy. Step 1 is the lower energy molecule, FADH2. Step 3 is the higher energy molecule, NADH. All right, now here's the one that might need to come up with some sort of memory thing. But what are the molecules and enzymes? So if you can do the molecules first, the enzymes are a lot easier. So the way that I'll remember this, if you can do the molecules, great. It's a little bit difficult. So the first one is going to be the acyl-CoA. The next one is going to be the trans fat. And then the next one's going to be hydroxy. And then the last one's going to be keto. And those are the key words. I didn't say that. That's why I'm just throwing them at you this time. And so ATHK, yeah. That's one that you're going to have to probably work on. I should have let you have active recall perhaps, but I wanted to just, if you can remember what came in is obviously the first guy. Trans, hydroxy, and keto. If you can remember those are unique parts of each name, and that's enough to get you through. And we'll give you the right information. Then the enzymes, we already know step 1 and step 3 are the energy producing steps, so they're going to be the dehydrogenases that are just named after the previous molecule, which is why we had that question first. And no one cares about the hydratase. Thiolase is the last one. A thiolase is something that breaks, it deals with sulfur, which makes this interesting, but it makes and breaks sulfur bonds. It's the last one. Thiolase is one that I'm afraid I don't have a memory trick for you. That's the pathway though. So
Aren't they cutting peptide bonds here?
they are cutting, no, these should be carbon-carbon bonds.
Okay.
So I'm trying to think of a helpful memorization way, but I don't have one that would make sense to anyone that was, human. So we'll leave it there. And then the other one, energy costs, which we did some questions on, so I'm not going to go ahead and review that again. Hopefully this was helpful. Do we have any questions before we close up and move on to Phys? Take a little break between the two. Question?
An engineer uses OHOT as a mnemonic for the enzymes. So the first one's oxidation, then hydration, oxidation, thiolase.
Oh, cool.
OHOT, oxidation, hydration, oxidation, thiolase. Thank you. And also FAD, since it has an F, is first.
So dehydrogenase is doing an oxidation reaction. In case you're wondering how that goes along, it's not naming the enzymes, it's just the chemical reaction type. Probably caught that, but just in case. Thanks. All right. Anything else?
You said an enol was what? Referred to what?
So enoil is it's the part of the name trans-enoil. I just remember that this is a trans fat. I don't remember saying specifically what an enoil is. If I did, I don't actually know. I know what an enol is, but
Enol is.
And an enol doesn't show up in this pathway, but if that's what your question was, an enol is a double bond with an alcohol. And so you have carbon, double bond carbon, and then somewhere else there's an alcohol group. And you would call that an ene because 2 bonds puts an E in the name, and then OH puts an ol at the end of a name. And so you'd call this something, something, something enol. But we're talking about enoil, and I don't know. Don't know what that is. So, all right, let's go ahead and take 5 or so, just to refresh ourselves, and then we'll launch into Phys. Thank you guys so much. I'm going to go ahead and grab a drink.
That's all it's going. With or without? She's busy during meditation. Because I had the one here. She's got a food, but I don't want to make sure. I'm gonna get her. We're gonna get her. She got the pimpers. Since October 1st.
Oh, you gotta learn that. I love
But my family said for Christmas. She looks like she lost weight. Who's that? Okay, they did. They look like my daughter lost weight. Who's that?
Oh.
I know she was. I'm gonna feed her.
Like, I ate, since I know her this
Yeah,
month,
I didn't
I
think
eat 3 times more than I used to.
But I
And I'm still like, not, well, I think I'm kind of low now, because you need to maintain your weight.
How are you doing?
It's.
I just want to lose weight, but. Something's like the 20 program. Yes.
When I exercise more,
Yeah.
or I do more, I eat more.
So they say that they
I do workouts, but studying a lot, after a while, your brain's done. It's not efficient.
Different.
Yeah.
Just read it.
My buddy's
The same
paragraph.
paragraph.
Told me, but I literally sometimes stay up. She's over 4 a.m. last night.
If it works for you.
Yeah.
Like, everyone has their thing.
I know, it's weird. I'm like, the more I study, I feel like I just got some extra stuff in or something.
Yeah, if I'm more interested.
Because we don't have a lot of time, and I'm just
You
like.
can't help so much.
Yeah.
Even the passive, like somewhere in the orientation or something, they say passive, but it doesn't work. Oh my God, so it works.
Yeah.
How many
Long hours.
You don't do 21?
Well,
No,
around.
I can't.
2 months sleep doesn't help me.
Because everybody else,
So I
like,
was
oh, I go to
trying
sleep
to do
and
3 to 5.
it's embedded in my, it doesn't. If I don't stay up the long hours, I go to sleep, I wake up.
I'm just saying.
I don't know. I don't even know.
I didn't sleep
No,
like a lot. So Taylor, I have a couple questions.
Yeah, sure.
Dr. Schmidt put out an inflex study guide. Should we study them?
He put out a study guide. Like, I can't really say I haven't used it, so I found that as long as I understood the concepts enough, that I felt like I could say, well, what if this happened? No, this would probably happen. Then I tended to be good.
Do you do any inflex like tutoring?
Because mine's a number of
I do, most of what I do for NCLEX review is actually kind of what we're doing now, except I think a little bit more to try and point into the details of connecting to other topics as well.
But would that be like?
Well, why was it?
query?
I don't know, I just always.
Yes, so,
Go get it.
here, I'll tell you what I do. I'll tell you what I do, that's probably, I'd be happy to help prep for NCLEX, yes. I do tend to do topics for NCLEX, but more helpful, what I did was I would set up the topic of an entire lecture, and I would have that topic preserved so that I could look back at that topic every now and then and see, oh, what's this topic, what do I know about it? I did that with Untitled personally, and so I would put in a slide that says beta-oxidation, what were the 3, phase 1, phase 2, phase 3. And I just hit that every now and then. Sometimes yeah, and so I just, whenever Anki told me to do it, I did it, and I found that I almost, it was really nice when that came around, it worked really, really well. So, if you don't do that, just having the topics with anything not Anki related, as long as they're refreshed, you get 5 weeks that are completely set aside where you can ask teachers to go into any topic you want. They have classes to help prep you, and you're doing nothing except 5 weeks of studying however you want with teachers available, with tutors available, and it's a 90+% pass rate because of how much time you have to do it, and they have brush up classes that are, and all that kind of stuff.
So do you have to pay for that?
Pay for Anki? Anki's free.
Anki's free?
Yeah, I think that there's like an Apple version or whatever that sometimes people see and then they buy it because that's the one that has a price tag. But if it's on a desktop, you can get it free everywhere, so don't pay for it.
Which one?
Funky.
Yeah.
Trying to
And
use
then also for
okay, I couldn't think of it.
immunology, can you test for us? Are you doing group sessions for immunology?
I am not doing group sessions for immunology. I'm happy to answer concept questions. I would need to brush up on detailed questions.
So
Are you gonna?
we don't need it? Wait, what are your tips for immunology class?
So immunology is one of those love it, hate it classes.
I hope I love it.
Go for that side. What I would do is I would find YouTube videos before going to his lecture and just watch them say very simply, here's, does he even tell you what he's gonna lecture on next? Does he have a syllabus? Okay. Watch a video on that topic, because immunology, if you haven't had it before, has a lot of new terms, and that's actually the harder part, is when the terms don't make sense to you. If the terms make sense, it's literally just saying, this talks to this, talks to this, talks to this, kills that. And it's really fascinating how that all works. But if you don't know the words of this, like if this doesn't make sense, then you get lost in the chain. So read the vocab.
Like when nothing makes sense.
Your choice.
Yeah. Pretty much.
Nothing, just figure out that.
And the other thing for immunology is once you got the vocab down, see if you can rudimentarily say, okay, skin has damage, these things get turned on, it goes that way. Big picture is where it can get easy to get lost in immuno, because we talk about the small picture over and over and over and over, and then you forget what organ you're in. And so it's like the signaling molecule signaling who, where, from what, and why. And so those questions make all the details have structure so they don't float off into oblivion. And yeah, big picture. Yeah, no worries. Okay, and thankfully with immuno, there are good videos out there. So if you can just know the name of the pathway, then that helps. I'm trying to remember if Armundo Hasadugan, if he has, it's fun to say. I know that he has good biochem. I don't remember if he had good immuno. Anyway, so that's what I got for now. So Phys. All right, so for this guy, any questions to start off with? And I'll also say up front, I did not have time to review my Phys before coming in too much. I did a little bit, mostly because I had some time with other people asking questions, and then I realized I need to review a little bit more. But, so have your slides ready, and we'll try to crunch through the concepts as best we can. Concepts aren't too bad. Details, we might consult slides. All right. Any questions to start off with? No? Okay. Then let's go ahead and say the major topics. Major topics are going to be platelet cascade. So where they come from, how they do their job. The other major topic is going to be clotting factors. So I'm going to call it the clotting factor cascade. And both of those fall underneath the whole clotting idea. They both help with clotting. Okay, so there's two separate cascades. Platelets doing their thing, clotting factors doing their thing. At the very end, they both work together with the fibrin that they both have either produced or are using. And so that's how they tie together to make a thing. But other than that, they're kind of separate cascades. We'll go into those. Next, separate. It's like that was not enough to fill up a lecture, apparently. And so he also now has blood flow. That is the letter B. Blood flow physiology. And so this is saying what is the travel course of blood, what are the dynamics of it, why does it move the way that it does, and
Yeah. So we're probably only going to get into clotting unless we have questions on the physiology, just because of the time. And by the way, the biochem physio 1 hour is probably going to be fluid, just so you guys know moving forward. So
hemostasis, is that everything to do with the blood?
yeah, hemostasis sounds, I believe that's referring mostly to
Prevention of blood loss.
clotting.
Oh.
And so, but all of this has to do with blood. So basically it's the blood lecture. All right, so platelet cascade. If we have, let's go ahead and throw the platelet cascade here. All right, we have, let's do this actually from the beginning. We have pluripotent stem cells. These are cells that have not decided what they're going to be, and so they can become a ton of different things. They have the potential to become many things. Pluri, plural, many. Potent, well, potent can be powerful, can also mean potential, is what we'll go with. So pluripotent stem cells. One of the things that they can become, a couple other things, are guys called myeloid. And we're doing all of this to see how platelets get made, just by the way. Myeloid stem cells, they can still become many different things, so they're still called stem cells, but now it's only myeloid type things. Myeloid is just a category. And then lymphoid stem cells are the other major category. Pluripotent can do a ton of stuff. This is two of them. So myeloid stem cells can become a frick ton of stuff that you find in the blood, erythrocytes, da-da-da-da-da, including megakaryocytes. And megakaryocytes make platelets. So they come down the myeloid stem cell line. The lymphoid stem cell line, in case you're curious, we were talking about immunology a little bit. Lymphoid makes pretty close to all the immune stuff. All right. Once platelets are released into the blood, they are just bouncing around, inactive. They don't stick to anything until they are activated. Platelets can be activated in a couple ways. A platelet that goes next to a damaged piece of blood vessel wall, we're just going to call this damaged over here, that has some collagen showing. And collagen plus von Willebrand factor will activate the platelet. We'll make the platelet now squiggly because it's all active and stuff.
And the von factor is just floating around.
So that's a good question. I'm trying to recall how it gets on top of the collagen. I think that it's released by the endothelial cells when they get damaged. That's what it is. So endothelial cells have von Willebrand factor inside of it. The other place you find von Willebrand factor is megakaryocytes will make it. But they keep it and stuff it inside the platelets. And it's inside the platelets, not outside the platelets. The platelets are waiting to see it outside of them to be activated. Make sense? Mm-hmm. So the von Willebrand factor came from the damaged endothelial cell that sticks to the collagen, which shouldn't be showing to the inside. It's damaged, so collagen, connective tissue, is showing to the blood, which shouldn't be happening. And so that's why von Willebrand factor sticks to that preferentially. And so collagen and von Willebrand factor, platelet sees those together outside of itself. Von Willebrand outside means turn on. Cool? So what does turning on mean for the platelet? Turning on means that it's going to dump a bunch of stuff out of itself, including ADP and thromboxane and let's see. I believe that it also throws out von Willebrand factor, and I am totally blanking on this. It's like, was it serotonin?
Serotonin.
Serotonin. All right. So, and these guys are going to activate other platelets. So other platelets that were just floating by, they never saw the collagen. They're going to have all these little granules come and talk to them, and therefore they turn on. And then they will release their granules. And so it becomes this whole cascade of turn on all the platelets in the area and make them all become active. Active also means sticky. So now they're all going to come together. Sticky. And they're going to make a bunch of platelets together. We'll just call it, right now it's just platelet aggregation. That's what this step is called. Platelet aggregation. Up here was activation. And once this finds its way, I've drawn it so that the injury is up here, but actually the signals managed to go and talk to platelets earlier. And so then this is actually floating down, and it will meet the wound and become a platelet plug. I'm going to move the wound down here, and it's a platelet plug as it fixes over the collagen there. This first guy actually stayed stuck to the collagen, and he's grabbing and making everyone around him sticky, and then he holds them in place. Does that make sense? All right. And so this would be called a platelet plug. Up to this point, this pathway has just been platelets. No clotting factors involved. For the next part, I'm just going to, right now, since we're in the platelet story, I'm just going to say clotting factor story happens. And at the end of the clotting factor story, it makes the piece that the platelets need. Because right now, they're kind of, well, they're platelets and they're sticky, and they're kind of gummy, they're not super tough. And so they can be, they're not able to hold the wound closed. If it stretches, they're not able to pull it together. And so they're just sort of a temporary plug. They're not very tough right now. So they need something that's going to make them tougher, and so that they can do a couple steps that we'll talk about. And that something is fibrin. So donated from the clotting factor cascade, the whole point, for the platelets at least, the whole point of it is to make fibrin. And that fibrin is going to be floating down through the blood, and it will come and join the platelet plug to make it into a clot. So it was a plug before, now it is a clot. Okay? And it's got nets of fibrin going all through the platelets, making it much tougher and much more stable. It keeps it from flying off and making so that you have an embolism, which could go and lodge in your brain or your lungs and cause problems. Keeps it there. It also makes so that as the wound heals, you can have the fibrin is going to go ahead and pull together and keep everything here and bring everything together, and that encourages wound healing. So think of the plug as that gummy stuff early after a wound before a scab, because that's what it is. And then when a scab forms, that's more towards clot, when you have fibrin there and it's tough. There's a couple other things like dehydration going on as well, but that's kind of the main difference. Early scabs you can just rub off. That's a platelet plug. Actual scabs have fibrin, so they stay nicely. All right, so that's kind of the platelet story. I feel like there was one other thing. Oh yes, clot and clot retraction. Clot retraction is just the clot getting smaller, because if it couldn't do that, the wound wouldn't be drugged together, and also, eventually you want this to go away so that it doesn't become an embolus. So you need to make it smaller as the wound gets smaller, and you also need to be able to chew it up, which is the last step, which is going to be fibrinolysis. Fibrin being chewed up. Fibrinolysis. Kind of ran out of space here, but the purple ones are the ones that happened after fibrin arrived. All right, and the for fibrinolysis to occur, there's a specific molecule. Rosie, do you happen to remember what that molecule was? Plasmin, wasn't it? Plasminogen and plasmin?
Yeah, plasmin.
Thanks. All right, so when we want the clot to go away, the last thing we release to chew it up is plasminogen becomes plasmin. And that chews up the clot.
Wait, can you say that again?
So we have a clot that we want to get rid of because all the healing is done. The body releases, the body takes plasminogen, which is always around, it's inactive, and then it cuts off a bit of it and turns it into plasmin, and plasmin goes ahead and dissolves the clot. They actually give, in some procedures, they'll give you plasmin. Actually, they give you the thing that cuts up plasmin. In your slides, do you guys have the name of the thing that cuts up plasminogen to plasmin? I think he wants you to know that.
And he gave us D-dimer and streptokinase, TPA.
TPA.
Yeah.
Awesome. TPA. That's what I think he wants you to know. TPA cuts up plasminogen to make it into plasmin, and that chews up the clot. And so in some procedures, when it's really dangerous for the person to have a clot, and it could be really serious, like a stroke, someone's got a clot that is blocking off blood supply to the brain, you need to get rid of that clot really, really fast. You might use TPA to make so that you chew up all clots in the body.
The TPA is tissue plasminogen activator.
You got it. Tissue plasminogen, I think it's activator. I don't think
They activate. Okay, and other than also the streptokinase.
It shows me it's a different thing, but it was active.
And plasminogen is
Yeah.
the name of the
Yeah.
clot, basically.
Plasminogen is the name of the inactive. It's always in the blood. It's not part of the clot. Plasminogen is just a molecule floating in the blood, waiting to be turned on, and then it'll chew up the clot really, really well. And I heard you were mentioning something about streptokinase. I don't remember. So there's going to be some details that I don't remember. I didn't have time to make sure I had everything.
No, streptokinase, if I can recall, is in the same class as TPA, but they're two different, but they work together. So
Okay.
like heparin and warfarin.
Oh, okay.
Yes.
So they're both acting on plasminogen?
Yeah.
Okay. And it's just two different ways to do the same job. Oh, cool. All right, streptokinase and TPA then. From Rosie, thank you.
Oh.
Thank you.
Streptokinase. Yeah. So, yeah, is there anything else from the slides or that you guys remember from lecture that you want to toss out? This is what I've got for this part. So, can we fill in any holes? Okay.
So what initiates from clot retraction to it just being chewed up?
So I don't know a particular signaling factor, but it's going to be as the wound heals, it will initiate clot retraction, as well as when the wound is completely healed, somehow it'll signal for the clot to be gotten rid of. It's based on the wound
And the
healing.
TPA is just floating in the body.
TPA is probably going to be, so this is a guess, I don't know this, it's probably in the endothelial cells because they know when the clot needs to be chewed up because they're right there. And so they would be the ones that are releasing TPA or strep kinase or something that turns on TPA from elsewhere. They'll start the cascade, in other words, is what I would guess. All right. All right. So for this, where do they come from? How do they get turned on? When does fibrin, and then all the stuff after fibrin. I like to go turned on down to the plug, and then fibrin stuff after that. If you can do each of those little stories, then that'll help you target where you need to work on, and if you can do all of them, then you're good. So.
Is the clotting factor cascade happening at the same time that platelet cascade is happening?
Yes. Yep. They are both happening simultaneously, parallel. And the last step of the clotting factor is fibrin. Last step we care about. Actually, I think it is the last step in any story. I don't know if there's an exception. I almost never dare say that, though. All right. So let's see what time it is. All right. Do we want to hit the clotting factor cascade, or do we want to do a brief review? What's more helpful for you guys? Cascade?
Yeah.
Okay. Review that stuff, and let's move on then. Clotting factor cascade. So, simultaneously, there are two clotting factor cascades that can happen. In other words, there are two ways to turn it on. One way to turn it on is for collagen to be exposed, which is, it has a name, it's called tissue factor or factor 3. Tissue factor, aka factor 3. And that's one way to turn it on, and it has its own little thing. The other way to turn it on, it starts with factor 12, and I'm trying to remember what the heck turns on factor 12. Anybody got that one? What turns on factor 12? Pop quiz.
Is it collagen?
Collagen, I think collagen, it's possible that collagen does turn it on. If you, tissue factor I thought was the one that dealt with that, but it's possible they both do. So if you could get a slide to confirm
I
that.
thought it was, okay, I think I'm getting it wrong. The activation of the 11 and 12 was by the subendothelial collagen. So that one was called collagen.
Collagen.
And then the first one is the extrinsic factor.
Yes.
And that's tissue factor, right?
So extrinsic is.
Yeah.
Thank you. Oh, it's because they both start like that. Okay. Thank you. All right. So this one is indeed, they're both from damage. Well, otherwise we wouldn't need a clot. This one's from collagen in particular. This is from endothelial cell, which has tissue factor. So it's just intrinsic to the endothelial cell. Thanks for that. Endothelial cell. I'm going to go ahead and, in this case, those are not enzymes. I'm just going to box the instigator. Okay, so we have two pathways. And when they named these pathways, plugs and clots form in the blood, right? And then they go up against the wall. It's kind of in the blood that it's going on, if you're going to say it was in anywhere. And so they named intrinsic, meaning inside the blood. Extrinsic, meaning outside the blood. So when they say intrinsic pathway, it's all these bits that are floating in the bloodstream. When they say extrinsic pathway, the second one on the right, that is the one that actually is dealing with cells, not in the bloodstream. So the bloodstream bumps up against it, but the pathway starts outside of there's actually a factor outside the bloodstream. Okay? Whereas this other one, factors might be turned on by bumping into things, but all the factors are floating in the blood. So, all in the blood, mostly in the blood, but there's one bit that isn't, so they named it that way. So, with this one, there's just a lot of things that I'm going to tell you how I remember it. Basically, it's kind of a memorize it thing, and then there's a little bit of understanding about positive feedback. So, 12 to 11, you're counting down. Then go ahead and swap so you're counting up. 9 to 10, and I'm going to stop using Roman numerals. So 12, 11, counting down. 9, 10, counting up. And then 10 is going to go ahead and get to our buddy prothrombin, who is going to be kind of our star for like who does all of the work. Everyone else is just trying to talk to him, or he talks to everyone else. So remember prothrombin / thrombin. It's the same molecule, you're just cutting a little bit of it off, so the name changes a little bit. Okay, 12, 11, 9, 10, prothrombin to thrombin. Okay, so each of these is turning on the next guy, and if they have a little lowercase a next to them, that just means that they're active. So 12 turns on 11, 11 turns on 9, 9 turns on 10, 10 turns on prothrombin, which for this one, it goes from prothrombin to thrombin. It also has the name of factor 2. And so you could also say 10 turns on 2 and turns it into 2A, but most people say prothrombin and thrombin because this is an important enough one that we use the name. Make sense so far? Okay. All right. Now, once you've got that pair, and you've arrived at prothrombin, then that's kind of most of the intrinsic pathway. Extrinsic pathway is going to have tissue factors sitting there until factor 7 is turns on 9. Awesome, thank you. I remember this one by 3 and 7 are just, I don't know if you guys are like, symmetry is beautiful and 10 is a nice number and all those sorts of things. 3 and 7 put together make a nice number. If you're not, insane that way, then bless you. You can remember that I'm insane and it makes 10. So these first 2 steps are intrinsic. These first 2 steps are extrinsic. And then we can call this the common pathway because everybody meets up at 9, 10, because 7 technically also turns on 10. It works on both of them. Clear? Okay, last thing to talk about then, thrombin. And this is the one that is likely to actually be, the stuff we talk about in this is more likely to be clinically relevant as well as have questions because it's clinically relevant. Good to understand all of this. Here's where we have thrombin doing its thing. Thrombin has 2 jobs. First one we've already talked about. It takes fibrinogen and turns it into fibrin. So fibrinogen is inactive. You'll notice that a lot of molecules, when they have gen at the end, it means it's an inactive form. The term for those molecules, all of them as a family, are called zymogens. They mean inactive things until they are clipped to be turned on. So fibrinogen is a zymogen, so it does nothing until thrombin clips it and turns it into just fibrin. And there is no way that that is even like visible. Brown. So that's one thing that it does. Then fibrin goes and does its thing down there. The other thing it does is it comes back and it turns on. You'll notice we skipped some numbers. We have factor 5 and factor 8. That thrombin is going to go ahead and turn on. Factor 5 and factor 8, factor 5 speeds up factor 10. So it just makes this whole common pathway is going to be sped up, is what we're seeing. The common pathway is going to be sped up by these guys. Common pathway is made of 9 and 10, so 9 and 10 are going to be sped up. 5 speeds up 10, 8 speeds up 9.
Taylor, real quick, so 10 activates 2?
Yeah, it would be 2A technically, but it's 2.
Okay.
Good question. Okay, and these two guys that speed up, 8 and 5, those guys are, this is what we would call positive feedback, because thrombin turns on things that make more thrombin, that turns on things that make more thrombin, and ad infinitum. So it's a positive feedback loop. If you don't have these, this whole thing gets slowed down and fibrin doesn't get made very well. Without these speed up bits, it's slow enough that we actually have a disease state, a couple disease states, depending on which ones are broken. Factor 8, the disease is called Hemophilia A. Factor 5 also has a disease, and I don't remember what that one's called, but it's a blood disease.
So hemophilia A is like lack of factor 8?
Exactly. All right. Any questions?
So,
That's good.
The positive feedback loop starts with thrombin.
Yeah.
Okay.
It's kind of hard to say a starting point for a loop, but if I had to name a starting point, it would be thrombin.
You wouldn't have that.
Mm-hmm.
Okay.
So. All right, let me ask you guys a few questions. Try to answer them without notes if you can, but either way. Which pathway is completely in the bloodstream? The intrinsic or the extrinsic pathway? Intrinsic, good. All right. What is the one factor that is not in the blood? All the factors are found in the blood except tissue factor. And I don't know if I said this. What is the number for tissue factor?
3.
3. Good. All right. What are the two things that thrombin does once it's turned on? It has two jobs.
Fibrin.
That's one, fibrinogen to fibrin.
And they create factors 5 and 8.
Turns on factors 5 and 8. Yes. 5 speeds up. What was that? Yeah. Which one does 5 speed up?
10.
10. And 8 speeds up?
9.
Okay. What was the other word you used for speeds up? Like the technical word for speeds up?
That's a great question. Más rápido. I don't know.
I thought you had a term for it. It wasn't activated. It was like, and it wasn't positive feedback.
Upregulates, enhances.
Oh yeah. Okay.
Yeah.
I get the point.
It's recorded. Okay. Because I don't know what I said. You think I track what comes out of my mouth? So much evidence against that. And disease. I just pointed at it. Which factor has the disease and what's its name? 8, Hemophilia A. All right. So the way that I would chunk this up to review, intrinsic pathway, extrinsic pathway, common pathway. So it's just what starts it, and then its little, so collagen, intrinsic is collagen 12-11. Good. Extrinsic is tissue factor and 7. Good. Then once I have those ones down, I can do the common pathway, which is just 9, 10 prothrombin. Okay? If you chunk it up that way, then it isn't a mess. And then you can say, what are the 2 parts of thrombin for your last question? Question 1, question 2, question 3. What happens? Question 4. So hopefully that's helpful. We did not get to blood flow physiology, so are there any questions on that? We're not going to go through the whole thing because I think we've hit basically time. But, yeah.
Not about that, but, so he gave us.
Or excuse me, which clotting factor, tissue factor?
Tissue?
3.
It's not.
Correct. Tissue factor would be that one. Any other questions? All right. Then thank you guys for coming, and I'll see you guys next week. Yeah, no worries. Catch you guys next week too.